Welcome to the 10-minute KQL reference guide. This guide is intended to consolidate the KQL operators in a single reference video and provide an explanation with at least one example per operator. Each operator can be found by either using the chapters in the video timeline or by clicking the time links tagged in the comment section of the video. If you need a quick refresher, this video serves as a single point of reference. If you're new to KQL, we recommend reviewing the KQL beginner playlist found on the channel. If you want a more in-depth breakdown of each operator with more use cases and homework assignments, then check out the intermediate and advanced playlists. We'll be using multiple free datasets to include a log analytics workspace found at aka.ms/lademo, an Azure Data Explorer environment found at kusto.azure.com/public free cluster, and kc7cyber.com, which uses ADX to simulate corporate networks, so you can practice your KQL skills solving cybersecurity investigation problems. The order of each KQL operator will be from basic to advanced. Let's begin writing our first query using the sign-in logs table. As we start to type in sign-in logs, we can see that we receive suggestions from the Intelisense feature. If we want to use this suggestion, we can hit the Tab key. We see that it completes the suggestion and enters a new line with a character at the beginning. This is called the pipe character, and it serves to take the output of the previous line and use it as an input to the current line. Let's type in take 10 in all lowercase letters, then click on the Run key. Take samples random records, and the number 10 represents how many records it will sample. If we scroll to the right, we can see all the field names, and we can see all the values for each record. This table is showing us all the interactive sign-in activity for our environment. Taking a sample helps us understand what fields are available and the different types of records produced. If we want to filter the dataset to only see records from GB for Great Britain, we can use a where statement. We can use one or more where statements to begin to filter down our massive dataset and see only the information that we're interested in. As we type in where in lowercase letters, we see Intelisense recommends it, so we can hit the tab and fill it in. After where, it expects the name of a field that we want to filter on. The name of the field is location with a capital L. If we want an exact match of GB, we can type in the double equals, which means an exact match to include correct spelling, spacing, and capitalization. Since we know we want GB with both letters capitalized, we can type it in either single or double quotes. We can type a new line with a pipe character and take 10 for another sample. As we scroll over to the location field, we see that only GBs are there, so we know our filter worked. If we wanted to type in more where statements, we could. We could also replace where with and. If we type in multiple where statements, all of the conditions must be true in order for the record to display. When we use and, the same thing applies. All conditions must be true for the record to display. We can also make a stylistic choice to indent ands for ease of readability. It's purely stylistic and has no bearing on how the query functions. When we use multiple ands and decide to place each one on a new line for ease of readability, we don't need to use a pipe character. What if we wanted to see both sign-ins from GB and sign-ins from the US? We could use OR. With OR, if either of the two conditions are true, it'll produce a record. When we run the query, we can see a lot of sign-ins from the US, but occasionally we see one from Great Britain. If we wanted to also see sign-ins from Canada, we could add another OR line. As you can see, adding a new line for each new condition can get old quickly and can make our query pretty long. If we have many conditions and we want to see records if any of them are true, just like an OR statement, we can use in. When we use in, we can use parentheses and place all of our conditions inside. When we run the query using in, we can see it works the same as multiple OR statements. We place a comma between each string, and we place quotes before and after each string value. We can either use single or double quotes, but we shouldn't mix them. When we use the double equals, or in, the capitalization matters. If we change the capitalization and run the query, we can see that it has no results found, because there were no exact matches. Sometimes we don't know the capitalization of what we're looking for, or they could have been entered into the database with different capitalizations. To make our query case insensitive, we can use the tilde symbol. It's located on the upper left of most keyboards and looks like a wavy horizontal line. When we place the tilde after in, it makes all of our conditions case insensitive. Now when we run the query, we get all of our results back. We can do the same test with double equals, but instead of double equals, just place a single equals followed by a tilde to make it case insensitive. If we take a sample from the customer table, we can see it provides all the customers for the Contoso company, and it has associated personal information. We can see there are a lot of fields. Oftentimes it's too much information and we just want to narrow down the fields to the ones we're interested in. In this case, project is useful. Project displays only the fields we want to see. If we're only interested in seeing the first name, last name, city, state, and country of each customer, we can project those fields. Intelisense identifies the field names so we can tab our way through to speed things up. Now that we've narrowed the data set, if we want to go back, or maybe we want to add another field, we can use the double slashes to comment out the line. When we use the double slash, it comments out everything to the right of the slashes and effectively takes it out of the query. The commented out sections turn green to let you know they're not being considered as part of the functioning query, as if the information to the right didn't exist. Maybe we want to add one more column with education level. We can uncomment the line, add the additional field name. When we run the query, we can see it populated the extra field. The order of the fields in the project line determine the order of the output. So if we want to change the order, we can manipulate it in the line. We can also place a comment before the query, or to the right of any particular line. This can be useful to remind us, or to inform others, if we share the query, what the purpose of the query is, or any areas that need to be filled in for the query to work properly. When we filter with where statements, sometimes we aren't sure what all the options are in each field, since many of the tables are large in size. One way to find out all the available options for a particular field so we know how to write our where statement is to use distinct. Distinct shows you all the unique values for a field. In this example, we want to see all the unique education values for the table. We type in distinct, then the name of the field, and it provides all the options available from the output dataset. Now we can select one or many of the options and filter using a where statement. When we view the output datasets, the records are often out of order and can be large and confusing. One way to place order and structure to the output dataset is to use sort. We could sort by a specific field or multiple fields. If we type in sort, then the name of the field, and run the query, the default sort type is descending. Descending is in reverse alphabetical order. When we sort by a time field, descending is the newest or latest time value. If we want to reverse the order, we can use ASC, which is short for ascending. If we want to sort by two fields, we can place a comma. Here we see it sorts by our first field, then sorts by our second field in groups. Before we showed how to take a sample of a table so we could see what's in it. If we have a string of information and we want to see where that may be located in our datasets, we can use search. Search uses a lot of resources, so be aware that it may time out if you're searching large databases. We can search a single table, or we can search multiple tables, and even all tables that we have access to. In this example, we'll try a broad search for a device name. Our goal is to identify what tables the device can be found in. When we look at the results, we see a new field of $table. This represents the name of the table the information was found in. We can then pivot to that table, take a sample, and begin to write our where statement to filter for that device. If we wanted to search for a string of information inside of a table, we can place the table name, then pipe in search in this way, and it shows the records with a match. Before we use double equals when we're filtering for an exact match of a string. Sometimes we don't know the full string and just know part of the string. In that case, we can use contains. Contains uses a lot more resources and processing power than double equals, so it's best to use a more efficient option when you can. If you're searching for a string using contains, be aware that it might not always be exactly what you're looking for. When you use contains, it's automatically case insensitive, so capitalization doesn't matter. Another option is to use has. Has leverages delimiters, which are a known set of characters that are recognized as a break in the string and can be used to start and stop each string search. This adds an additional layer of precision above what contains offers. And just like contains, has is not case sensitive. Here are some examples of delimiters. In this example, we want to find URLs that have COM. The period and the space after the M in COM both serve as delimiters to isolate the string. If we use contains, we would also get all of these URLs, but we'd also get many other string values that contain COM in the words that potentially ended in a different top-level domain, like .uk. Another option that works in a similar way to contains is starts with and ends with. If the strings you're looking for start with a set of characters, letters, or numbers to include delimiters, you can use start with. The same goes with ends with. In KQL, the exclamation point represents not or doesn't. If we want to find strings that don't start with, don't end with, or don't equal, we can use the exclamation point. Here are some examples of using the exclamation point with where statements for filtering. When we produce results in a dataset, we can see the count of records here, and the time it took to run the query here. If we wanted an output dataset that only included the count, we can type it like this. Before we talked about strings, we can also manipulate integers, which are whole numbers. It's possible to have letters, special characters, or numbers in your strings, but there are certain things you can't do with strings, like math problems. When we're working with integers, we can perform math. When we type in a string, we have to use either single or double quotes. When we use integers, we don't need quotes. In this case, we want to filter this field for values greater than 4. In this example, we want to filter for values less than 2. And in this example, we want to filter for values of greater than or equal to 2. If you aren't sure whether a field contains strings, integers, or other data types, you can use getschema. The schema helps us understand the structure of the table to include what data types are associated with each field. A key part of filtering is narrowing down the time span of the logs. Here you can see the GUI is set for 24 hours, so by default the query produces results for the last day. If we need logs for the last week, we can change the GUI settings. And if we need logs from and to specific dates or times, we can also set that in the GUI. Keep in mind the data retention settings for your environment dictate how far back you can query the data. While you can set the date time in the GUI, it's best practice to set it in the query. So if you share or reuse the query later, the date ranges are preset in the query, and there's no guesswork or manual setting required that could produce an error. There are several ways to set the time span in the query. One way is to use a go. If we want to see logs for the last week, we can type in the name of the field containing the date time we want to filter on, then type in greater than or equal to in a go 7D. We're saying that from a point in time 7 days ago, we want to see records greater than that marker. When we use greater than with a date-time data type, it means more recent or later. If we only wanted to see records older than a week, we could use the lesser than symbol. Common time options are S for second, M for minutes, H for hours, and D for days. Keep in mind there are no week, month, or year options. So if you wanted to see records from 2 months ago, you could use 60D, assuming you had logs retained for that long. A go is useful if you want to go back a specified time. But every time you run the query, you'll get different results because the period defined as precisely 7 days ago is constantly moving as time moves forward. When you need to start or finish your query at a precise date time every time you run the query, you can use between. Between expects a start and end date time, but you can also reference other functions such as now. Keep in mind that if your selected time frame is before your log retention period, you may get partial or no results at all. When we type in the date and time, KQL recognizes many formats. It's common to just pick a format that you can remember and that works best for you and stick with it. In this example, let's use year, month, day, hour, minute, second format. This format is nice because working from left to right, it starts with the largest time value, which is a year, and progressively works towards the smallest time value, which is 1 second. And it has a capital T in between the date and the time. When we use between, we place our times in parentheses, and we place 2 dots in between the start and the finish date time. When we run this query, we can see that all the dates and times fall within the time span that we've defined. Remember, the first date and time must be older than the second date time, otherwise the query will fail. Here's another option. If we want to see all records starting from one date time and finishing right now, we can use the now function. If you use this, keep in mind that the results will continue to change as additional records are logged, so the results of the query today will be different than the results of the query tomorrow. We can also choose just the time and not the date. If we do this, it's assumed that you're referencing today. It's also an option to use just the date. If you do, it references midnight on the morning of that date. In this query, it is not providing a dataset output beginning with the 5th and ending on the end of the 7th. Instead, it's providing one beginning on the 5th to the beginning of the 7th. Because date times generally require 3 sets of parentheses, they can be a little confusing. Just remember all of your dates and times are encapsulated in one set of parentheses, and each individual date time has a second set. Also remember when working with times in KQL logs They're generally kept in universal time, or UTC. This can also be referred to as Zulu time, or Greenwich Mean Time. This universal time is often used because companies are global. They span multiple time zones, so logs stored will speak a common language that anyone in the company can understand no matter what their geography is. We've already discussed using take to get a sample of the data and using sort to organize the data. Sometimes we want the first 10 or first 100 records from the output dataset, and we don't want random records that are associated with take. In this case, you can use top. When we use take, we just put a number after it. When we use top, we place by after it. Then the field we're interested in. Think of it like a mix between take and sort. You can also use ASC or DESC after for ascending and descending order. Next up, we have extend. We use project to only display the fields we're interested in. And if we want to create a brand new field, we can use extend. Extend is powerful because you can define the parameters of what the field should be, and you can get creative with that definition. Here we're taking a sample of the perf table, used to see performance metrics for Azure virtual machines. We see the time-generated field in UTC. What if we live on the west coast of America, and right now the time difference from UTC is -7 hours? We want to display Pacific Standard Time in its own column. We can start by piping in extend. Next, we type in the name of the new field that we're creating. We'll just call it PST. We then use a single equals. This will help define what PST will contain. We want it to contain the time-generated field -7 hours, so we can type it in just like this. When we run the query, we can see the difference between the two fields is 7 hours. Summarizations are great for answering big picture questions about your dataset. They're useful for investigations, and they also facilitate presenting your information in charts and graphs. In this example, we're looking at authentication events. If we wanted to see the unique result types, we could use distinct in this way. Here we see that there are only 2 distinct result types for authentication. We can change distinct to summarize to help us enrich this data. There are many functions we can use with summarize to help us with the enrichment. Here we're adding a count function for each result type to enrich the distinct values. In this case, we placed our enrichment function to the left of the by and the fields we wanted distinct values of to the right. If we want to summarize by more than one field, such as a result and username, we can place additional fields to the right of by. Each count is of the unique combination of both fields. We can also layer in multiple functions to enrich our data. We can add the earliest and latest date-time values for each username and result type. We can see that the first user has a total of 17 failed login attempts from August 13th through September 9th. And they had 24 successful sign-ins in the same period. We can also layer in the make set function to list out all the IP addresses associated with both failed and successful authentications. This can help us identify any potential anomalies in the login activity. We can use the dcount function when we need a distinct count of unique objects in a given field. The count field on the left is saying this user had 24 successful logins. The dcount field is saying there are 2 unique IPs associated with successful logins for that person. You can start to see how powerful summarizations can be in answering questions we have in our dataset. In our query, we have min and max time values. We may have a series of records, but only want the most recent record for each day. And we don't need the other values represented. The argmax function can help us out. In this example, it shows us the most recent successful and failed login for each username. Argmax requires 2 arguments. The first is the field you want the target for the time value. And the second is what fields you want to display. If you choose the asterisk, you'll display all available fields. If we only need the timestamp, host name, and username fields, we could just type them in, just like we would be using in project. We also want to introduce the bin function. In previous queries, we provided enrichments for a wide range of time domains. We can also place the time values into buckets of 1 minute, 1 hour, 1 day, 1 week, or any other time bucket we choose. Let's narrow our focus to the first user. Our goal here is to identify how many sign-ins occurred each day. We can use the bin function to break the summarized count by day, like this. We can see that the activity took place on 4 distinct days. The bin function wants 2 arguments. The first is the field to create the bin buckets in, and the second is how much time each bucket should represent. If we wanted to visualize this data in charts and graphs, we could use render. We see there are many types of charts and graphs to choose from, so let's pick time chart. We can see it plots the number of login attempts by day. If we wanted to add additional resolution, we could change the bucket size from 1 day to 1 hour. This shows us a more precise window for the activity. We can also look at this data in different chart and graph types. Lastly, we can use the countif function if we only want the count under certain circumstances that we define. In this case, it will only provide a count if the result is a successful login. Let's move on to the topic of variables. Variables lock in a value or even an entire subquery into memory for the life of a query. The same variable can be used multiple times in the same query, but can only be called after the variable is declared. To create a variable in KQL, we use let. We then define the name of the variable. The name should help you or others understand what the variable represents. Good code reads like a book, and you can look back a year from now, having forgotten exactly what the query intended to do, and easily understand the output it produces. When you name your variable, avoid using names of existing fields. Some people like to place an underscore before the variable. Others like to make the first letter lowercase and other descriptive words uppercase. Pick a method that works for you and take a look at how others write their queries. Let's go back to one of our previous queries. If we wanted to filter for distinct counts of 3 or more, we could just place a where line, like this. Let's take the value of 3 and make it into a variable. Remember to add a semicolon at the end of the variable, which locks it into place. Now replace the number 3 in the where line with the variable name. You can see that once the variable is set, it displays as an option in Intelisense. When we run the query, we see the results haven't changed. Now let's modify this query to see only exact values of 3 distinct IPs. We can see something unusual. The devices that are not local admins are being authenticated to by the same IP addresses beginning with 104 and 87. If we get rid of the local admin devices, these authentication events need to be investigated more. If we need to take this data and reference other tables, we have a couple of options. We can join the 2 tables, or we can use techniques called chaining and pivoting. Let's say we want to take the user names from this dataset and pivot to employees table, so we can see more information about these 7 employees. First, let's use distinct to provide a single field with nothing but usernames. Now let's set this entire query as a variable. We created a variable called users, and we placed the semicolon at the end of our query. To make sure this variable works, we can simply call the variable on the next line to test it out. Perfect, it provides us the list of 7 users. Now let's go to the employees table. Let's make a where line that filters for usernames that are in our variable. We can use in, then place the name of the variable in parentheses. In this case, in is like using an or statement. So if any values in our variable are true, the record will display in the output. We can see the roles of these individuals are all network admins or operation managers. This activity is still suspicious to us, so we may want to pivot another time to identify activity on each device. We can use distinct to identify each host name. Then we can set this subquery as its own variable as we move to the next table to look at device activity. We can see that all 7 devices have the same discovery commands performed that an attacker may use for lateral movement during an attack. We definitely want to look at activity for these 7 devices more carefully. We can see that chaining multiple let statements together as we pivot from one table to the next helps us branch our investigation and dive deeper into multiple areas of new discoveries. If we have a variable that contains multiple values, we can use packarray. If we want to see if any of these values are found in a field using delimiters, we can use hasAny. If we wanted to see how many devices had all 5 of our discovery commands in the process command line, we can use hasAll. In this case, none of the 8 devices had all 5 discovery commands in their command line. If you find this content valuable, please give the video a like. And if you want more KQL content, click the subscribe button with the notification bell. Let's transition to joins. When we have 2 tables that we want to merge on a similar field, we can use joins. The common field is called a key. Let's show a basic example of a join so you can visualize the concept. The email table shows inbound and outbound emails. We know the employees table shows details of each employee, including their email address. What if we want to enrich the email table with additional information like the sender's device, IP, or role? In this case, the common field on both tables is the email address. Let's just focus first on the sender field of the email table. When we look at the employees table, we see the email address field name is email_ADDR, which is different. We can still join these 2 tables in this situation. If we're only interested in adding a few fields from the employee table, we can first start off by writing a query that displays only the information we want to join to the email table. Now to join this data with the email table, we use join. Then add the name of the second table in parentheses. Then we type on. After on, we define the key that we want to join on. If the field names in both tables are the same, we can simply type it in. But if they're different, like in this case, we define the field name of the first table, then the field name of the second table that will be used as keys. When we join, the first table we introduce is referred to as the left table, and the second table we introduce is referred to as the right table. So in this case, employees is the left table, and email is the right table. Let's run this query and see if the join worked. We can see that all the emails sent by our employees with the enrichments of the IP address, host name, and role information. This is a useful tool for collecting all the information you need in one place, so you can manipulate and filter it more effectively. There are many kinds of joins, and changing the type of the join will often change the output of your query significantly. The best way to visualize joins is to use a Venn diagram. KQL has 4 primary join types: the inner, outer, semi, and anti-join. Inner joins show results for key matches. Outer joins show key matches, but also show records that are not a match on one or more table that we define. Semi-joins first match the keys, then only show matched records from one table. Anti-joins first match the keys, but only display records that are not a key match. Each primary category has subcategories. The inner unique type is the default in KQL. It first deduplicates records on the left table and then displays key matches from the right table. If we don't define a key type in our query, like in the previous example, KQL will default to the inner unique join type. The inner join shows all records from both the left and right tables with a key match, and it does not deduplicate any tables. The inner join type is the default type in the SQL language. While inner joins only show records with key matches from both tables, outer joins show the key matches and include records that are not matched. There are three types of outer joins: a left outer, right outer, and full outer. A left outer will show you all the inner matches, plus add records from the left table that are not a match. A right outer will show all inner matches, plus add records from the right table that are not a match. And a full outer will show all records with matches and records from both tables without a match. A semi-join first calculates key matches in the same way as an inner join type, but it then discards values from one of the tables of choosing. A left semi-join starts with all the inner key matches from both tables, but it only shows the matching key values from the left table. A right semi-join starts with all the inner key matches from both tables, but only shows the matching key values from the right table. This is handy if you don't have a need for joining two data sets and only want to work with one table, but you want to identify the matches from a second table. Lastly, we have an anti-join. Anti-joins are similar to a semi-join in that they only produce records from one table. But instead of showing records with key matches, the anti-join only shows records that don't match. In a right anti-join, first all key values are matched. Whatever is remaining from the right table that is not a match is displayed as the output, with the opposite for the left anti-join. The anti-join is great for identifying all the outliers that don't have a key match. It may be hard to understand use cases for each join type, so we'll run through a few examples. In our first example, we have our employees table, which shows IPs for each device, and we have outbound network events that also has IP addresses. If we only want to see the outbound network traffic from devices not directly assigned to individuals, we could use an anti-join. In this case, we place the employees table first, so it's our left table. We place our outbound network events table second, so it's our right table. We can place kind equals, then define the join type. In this case, we want to use a right anti, which will show us records only from the outbound network events table that do not match with IPs listed on the employees table. On the next query, we have our employees table and our net flow table that shows network traffic logs. We want to first match network source traffic to all of our employee devices, but only display net flow from the matches. And we don't need to see any data from our employees table. In this case, a semi-join would be best. If we change the kind to right outer, we can see the number of records changed. And also some fields on the left are blank. Those represent records that did not have an IP match on the employees table. But since it's a right outer, all of the non-matches on the right table are still displayed. If you have multiple cloud tenants and you have the same tables in multiple tenants, the union is perfect for merging them in a single place. As an example, if you want to merge sign-in logs from one tenant with sign-in logs from a second tenant, the union would be the best option. Also, if you wanted to merge interactive sign-ins with service principal sign-ins, you could use a union. If you chose to union on two tables that do not have the same general schema, you'll have many blank cells. As an example, if we wanted to union device process events with file creation events, so we could have a unified sequential timeline of all processes executed on a device next to the files that were created on the device, we could union those tables. This can also help us in our investigation if we filter down to a narrow time frame of known malicious activity. We could see which files were created as a result of processes executed. Sometimes we need to export our output into a CSV file. We can do this using export to CSV, so we can manipulate the data in other programs. We may also want to bring in data from external sources. To do this, we can use external data. In this example, if we go to the following website, we can see a list of Tor nodes. In this example, we want to see if we have any inbound traffic from one of these nodes. First, we can create a variable using external data. We know from looking at the data that it's a single field of IPs, so we can define the field name as IP and cast it to a string data type. We then place brackets and use the @ symbol, then place our URL in quotes. We finalize our let statement with a semicolon. Before we go any further, let's call our variable and make sure it pulls the data without errors. We see it worked with over 1,000 IPs. Now let's pull up our inbound network events table and see if any IPs are in our Tor list. We don't see any of the IPs in our list, which is great. But this may be an alert we want to set and be notified of if any positive hits occur. Let's transition to data types in KQL. We'll refer to our data sets with fields running in vertical columns and records running in horizontal rows. We can use getschema to identify the data type of each field of the table. Even though the data types are defined, we can change them as needed to help us answer questions. There are limitations on what you can do with some data types, and other data types open new functions and capabilities to more easily perform tasks. Here's a list of the KQL data types. Bool is short for Boolean, which refers to a field that either has a true, false, or null value. You may want to write a query with a true-false value for a certain condition. In this example, we're looking at an email table showing inbound and outbound emails of the fictitious company. We'll extend a new field titled isExternal that will first look at the subject line, and if it begins with external in brackets, it will be defined as true. The date-time data type represents an instance of time. Although it's normally expressed as a date followed by a time, it could just be the date or just the time. Keep in mind that Kusto's default is to display in UTC, so if you need a specific time zone, generally it should be changed. If you want to review date-time options in depth, review to Lesson 9 of the Beginner Series. The decimal data type is a 128-bit length decimal number. While this is an available data type to use, it's more common to see decimals used in a real data type. The decimal data type is more precise in math equations than other options, but it's slower in processing time. So it may be a better option when precision is important and in niche use cases. The dynamic data type is unique in that it can take on any of the scalar data types such as bool, int, long, reals, or strings. JavaScript object notation or JSONs, which are displayed in key value pairs, are often represented as a string data type. And to more easily manipulate the contents, we change them to a dynamic data type. Sometimes they're stored in the database and they're already in a dynamic data type. So it's best to look at the data type before manipulating these types of objects. Deciding to switch to a dynamic data type can unlock additional capabilities in our queries, but it can also restrict the use of some operators and functions. So switching to dynamic has pros and cons. As an example, using distinct and summarize will throw an error if used on fields with dynamic data types. The GUID data type isn't very common in KQL, but it represents a globally unique identifier represented like this. Oftentimes you'll see GUIDs simply represented as string data types. When we think of numbers, they can come in many forms. We already talked about the decimal data type. Another data type for whole numbers is an int, which is short for integer. The int type is 32 bits in size and represents whole numbers without decimals. If there's a value with decimals and the data type is set to integer, it will round down to the next whole number. For larger whole numbers, you can use a long data type, which is 64 bits in size. While you see long data types more often than GUID data types, they're still not used that much, unless it's a specialty use case that requires them. Real data types are also 64 bits in size, but they allow for a decimal point, and may be more commonly seen over a decimal type. The most common data type is a string. It can represent a sequence of Unicode characters. Individual characters in a string can be letters, numbers, and symbols. Strings are placed in quotes. KQL has special characters that can't be used inside of a string. As an example, if you want to use a quote as part of a string, normally it would be recognized as the end of the string. We can use escape characters so it becomes part of the string literal. As an example, I want to print KQL as very intuitive, but I want intuitive to be surrounded by quotes when it prints. If I use a special character, such as a quote in a string, I use a backslash as an escape character to make it part of the string output. Time span data types measure the length of time between two time markers. If you have two different time fields in a query, and you want to identify the difference between the two, the output will be in a time span format. This can be useful if you want to identify how long ago something happened from the time the query ran. Sometimes the field has a record with no values in it. If the data type is a string, then the field is considered empty. If the data type is anything other than a string, the field is considered null in KQL. In this example, we're creating a new field called isempty and using the isempty function to identify a Boolean true-false value, whether the verged field is empty or not. You can also use isNull depending on the data type. There's also functions for isNotEmpty or isNotNull, depending on your use case. Casting is a term used when we change from one data type to another. We may do this so we can perform a math problem, or it may be so we can use a special function that only works with a particular data type. Sometimes we cast to one data type so we can manipulate the data, and then we cast back to the original data type to present it. When we cast to a new data type, we typically use this general format. Keep in mind that there are additional functions like parse JSON that don't follow the typical formatting, but they also cast to a different data type. In this example, we're looking at the network flow data for a fictitious company. When we look at the schema, we see a mix of date-time, string, and integer data types. If we wanted to change the bytes field to a string data type, we can cast it like this. And when we look at the schema again, we can see that it changed from an integer to a string data type. In this example, I have 5 fields projected. I see the status and device detail fields are JSON objects, full of key value pairs, in curly braces. When we look at the schema, we can confirm those 2 fields are a dynamic data type. We want to use summarize so we can get a count of each combination of the fields. When we try to summarize, we get an error because of the dynamic data type. When we cast both data types to string, then the summarization works. Remember that JSONs are key value pairs that are in curly braces with objects separated by commas. Many times these JSON objects are stored in the database as a dynamic data type, just like our previous example. But you can also find them stored as a string data type. While it's possible to parse the data we want with either a string or dynamic data type, it's easier to do it with dynamic. When we examine the JSON within the status field, we see it has 2 keys. The first is the error code, and the second is the failure reason. We also see that sometimes there's only 1 key, and other times there are more than 2 keys, including an additional details key. If we're only interested in extracting the error code key from the JSON and placing it into its own field, we can. Or if we want, we can take all the keys and make them into their own fields. The first parsing technique we'll teach is the easiest, but it uses the most amount of resources, and it's the least efficient. If you want to make all the keys inside a dynamic JSON object into their own individual fields, you can use evaluate bag unpack. In this case, you can think of the dynamic JSON as a bag, and we want to unpack each item from the bag into its own column. If you try to use bag unpack on a string, it will fail. So be sure to cast the JSON object to a dynamic data type if needed before using bag unpack. Also, each item placed in the bag can have its own unique data type. Just because the JSON object is cast to a dynamic doesn't mean all the objects inside retain the dynamic data type when taken out of the property bag. So let's go back to our original 5 fields, where we know 2 of the fields are dynamic JSON objects. Let's type in evaluate bag unpack. Then we'll place the name of the field we want to parse out in the parentheses. When we execute the query, we see the original 4 fields on the left haven't changed, but as we scroll right, we see all the keys that were inside the JSON associated with a status field are now parsed into their own individual fields. We should also take note that the original status field is no longer present. Once the information is parsed, it can then be queried. In this example, we want to only see records where the parsed out error code field is not 0. Before we parse the keys in the status field, the field was a dynamic data type. If you look at the schema after using bag unpack, we can see the device detail field with our second JSON is still in dynamic. But the 3 newly created fields that represent the keys that used to be in the status field are in a string or long data type after taking them out of the bag. Now let's use bag unpack on the device detail field to parse the JSON. When we scroll to the right, we see that all the keys from both dynamic JSONs are now in their own fields. When we look at the schema, we also see the data types of the keys inside both JSONs have still retained their original values once unpacked. One thing to watch out for is duplication of field names. If the table already includes an exact match of the key name you're trying to unpack, it will produce an error. In this example below, we have the same 5 fields we did before, but instead of the user agent field, we change the name to error code, because it's one of the key names inside the dynamic JSON object in the status field. If we try to use bag unpacked on the status field, we get an error now, because it can't produce a second field with the exact same name, unless we tell it how to handle that error. If you receive an error like this, it can be resolved by adding a prefix to all the parsed out fields. We can add a comma after the status field name, add quotes, and then add something easy like an underscore character. When we execute the query, we no longer see an error, and all the newly parsed out fields associated with a status JSON all have an underscore prefix. You aren't limited to an underscore prefix. It may add value if you name the prefix as the original field name to help you remember where each field came from. This can be especially useful when you have more than one JSON object to parse. Since the objects inside the property bag retain their data type when taken out of the bag, we may have a use case where we want to cast a new data type as we're taking them out of the bag. In this example, we have the device detail field that has a dynamic JSON. If we wanted to change 3 keys to a dynamic data type as they were taken out of the property bag, we could do it like this. When we look at the schema, we can now see that all 3 fields are cast to dynamic data types. Sometimes you have a JSON object which has key value pairs and curly braces, and it's stored as a string data type. To leverage many of the useful parsing functions in KQL, the first step is to cast the JSON to a dynamic data type. We can do this by either using parse JSON or todynamic. Both serve the same general function in preparing the objects for parsing or manipulating as a dynamic data type. In this example, we have two fields that contain JSON objects. As we look at the schema, we see that the status field is set as a dynamic data type, and the device details field is set as a string data type. In this example, we want to take a single key from inside the status JSON and make it into its own field. Remember, if we want to create a new field in the table that doesn't already exist, we can use extend. In this case, let's extend the error code key and make it its own field. This will create a new field called error. When we define what the new field will contain, we can reference the status field first, use a period, then reference the key inside of the JSON that we want to parse into the new field. When we execute this query, we see that the newly created error field contains the error code. We see the status field containing the original dynamic JSON is still present. And when we look inside of the JSON objects in each record, we can see the error code key value pairs match the new error code field. When we examine the schema, we see that the original status and device detail fields haven't changed, and the newly created error field is set to a dynamic data type. Remember, in the last session, when we used evaluate bag unpack, the items kept their original data types when taken out of the bag. But using this method of casting from a string to a dynamic data type, the data type of each key value pairs becomes dynamic. If we wanted to summarize or use distinct, we would have to cast to a different data type. In this example, if we want to cast to an integer, we could do it like this. If you remember, the device detail field is in a string data type. Let's see what happens when we try to pick a key to extend. Let's choose the first key of device ID. We get an error. It fails because the JSON object is in a string data type, and it must be set to a dynamic type to use this type of parsing syntax. In this case, we can use parse JSON or todynamic to cast to a dynamic data type. We'll create a new field called dynamic device detail. When we run the query, we can see it duplicates the device detail field. But when we check the schema, we can see that the parse JSON function simply changed the data type of the same JSON object from string to dynamic, unlocking the dynamic syntax for us to use. If we go back, we can also use todynamic to do the same thing. Parse JSON and todynamic are synonymous in the same way that sort by and order by are synonymous. Now that we have the device detail field in a dynamic data type, we can easily take one of the keys and make it into its own field. We can see that most of the fields are empty, and only a few have PII removed as values. If we wanted to now parse the second key of operating system, we can use the same method. When we run the query, we can see the operating system field is parsed. In the last examples, we used extend to create a new field. Let's go back to our original two JSON objects and use an alternate approach using project. Remember, the status field is already set to a dynamic data type. In this example, we want to project our two main JSON objects, plus we want to project the error code key as a new field. This worked in the same way that extend created a new field, except we accomplished the same thing using project alone. You can see that by casting to a dynamic data type in KQL, you can easily parse and manipulate JSON objects using either bag unpack, extend, or project, depending on your preference or your use case. We also see that when we extend or project, we may need to cast the newly created fields to a data type that we can better manipulate later in the query, as we cast back to something other than dynamic, such as a string or integer. We also want to show some use cases where you may receive an error trying to parse a JSON. In this example, we've projected the status field and authentication details field from the sign-in logs table. When we look at the schema, we see the status field that was used in our previous examples is dynamic, and the authentication details field is a string. Using the previous steps, we can try to cast the authentication details field to a dynamic data type using parse JSON. Then try evaluate bag unpack. When we do this, we see that it doesn't unpack any keys into their own fields. When we look closer at each record, we see the curly braces and the key value pairs associated with a JSON. But we also see brackets encasing the JSON in the authentication details field, but not in the status field. These brackets provide an additional challenge to navigate when parsing. The brackets identify an array, which is a collection of elements stored together. In previous lessons, we used pack array when creating variables with multiple values. In those use cases, we made our own array. Now we need to find a way to remove objects from the array or otherwise manipulate the array so that we can parse the items inside of it. In this case, the JSON object, full of key value pairs, surrounded by curly braces, is the object inside of the array. It's also possible to have multiple JSON objects inside of a single array. Before we discuss how to parse these, we want to cover the topic of indexing. In this simple example, we have an array with 3 elements in it. In KQL, the first element in the array is considered at index position 0. In this case, it's the string test. The number 52 is considered at index 1, and the last element of desktop 1, 2, 3, 4 is at index position 2. When we represent these index values in the query, we use brackets. If we wanted to reference the second element of the array, we can use the number 1 surrounded by brackets, which in this example represents the number 52. When we look at the schema, we see the authentication details field is a string data type. First, let's cast it to a dynamic, so we can try to manipulate it more easily. When we look at the schema, we verify that both fields are now dynamic. Let's try our normal extension method and see what happens. It does make a new field called test, but there's no visible values in the field, so this didn't work for us. Let's take a closer look at this array. When we expand one of our records, we see our 2 fields, and when we expand our authentication details field that we're trying to parse, we see a 0 and a 1. These represent the elements inside of the array. The first is at position 0, and the second is at position 1. There are 2 separate JSON objects in this array. Before we can parse it, we need to identify which element within the array we want to parse. We can do this by adding the element index at the end of the field name. Here we add a 0 in brackets to represent the first JSON in the array. Remember, the first object in an array is indexed at position 0, and the second object is positioned at index 1. When we execute this query, we can see it successfully parsed the key that we're referencing. We learned that even if we have a JSON inside of an array, we can still make sure that the field is dynamic, then we can identify the element in the array we want to parse from, and lastly, identify the key we want to parse. Now let's show an alternative method to work with arrays. We know that the authentication details field has an array with 2 elements, both of which are JSON objects. We can take each element out of the array and make it into its own record by using mvexpand. Before we show mvexpand, we want to refresh on a concept in the intermediate session. We use summarize along with makeSet to take values from multiple records and compress them into a set which is displayed horizontally in one record. In essence, with the array problem set, we can use mvexpand to do the reverse. We can take items that are compressed horizontally into one record, and we can make them into their own individual records stacked vertically. The MV in mvexpand stands for multi-value, and in this case, we have 2 JSON objects or values that we want to expand vertically. To use mvexpand, the fields need to be in a dynamic data type. Next, let's use mvexpand and place the name of the field we want to expand in parentheses. When we execute this query, we now see that the brackets that used to encase the two JSON objects are now gone, and each JSON is in its own record without brackets. If you look closely, there are duplicated time fields for every two records, because those time fields were present in both JSON objects. Now we can select a key inside of the JSON to parse using extend. We'll make a new field called auth method that will show the authentication method detail key. When we execute this query, we see that the value is in every other record, because that particular key was only in the first JSON object and not in the second JSON of each array. When using mvexpand, you may find that some arrays may have 10 or more objects that are extracted. When this happens, any fields in the record that are constants will be duplicated, and any variables associated with the expansion process will be new in each record. Depending on the use case, you may need to summarize the data after using mvexpand. Now that we have several ways to parse JSONs that are part of an array, let's talk about nested JSONs. In the last example, we had an array that contained two separate JSON objects. It's possible to have a JSON object that has a JSON inside of the JSON. This is called a nested JSON. To better understand the concept, we created our own test dataset. When we take a look at this output example, we see a single JSON that has the first key value pair, which looks like what we're used to seeing, and a second key, which has a nested JSON. Inside the nested JSON are additional key value pairs. While this example has one layer of nesting, it's possible to have multiple layers of nesting. We casted this field to a dynamic data type, so it's already ready for parsing. First, let's extend key 1 like we normally would. We can see that it works. So now let's try to extract values from nested keys. We can see the parse worked. We simply added a second period, which identifies the nested key to parse. If we wanted to extend the second nested key, we could use the same method. Let's move on to parsing strings. First, let's have a look at the email logs by taking a sample. This shows basic information on email activity in the company. And the far right column, titled Link, has the URL to embedded links within each email. For our first example, let's isolate that field so we can practice parsing it by using distinct. As we look at the schema, we can see that it's in a string data type, which is perfect for our parsing functions. If we want to parse out only the domain from each link, we can use parse URL. We can create a new field using extend, title it with the appropriate name, then define what's in the new field using parse URL. We place the name of the field we want to parse within the parentheses. When we execute this query, we see that a JSON is created which has taken the URL from the link and parsed it into standardized key value pairs. If we examine the keys, we see the first one, titled scheme, displays whether it's in HTTP or HTTPS. We can see the second key of host has the domain. We can see that some but not all URLs have a path leading to a file name. For those, the path is parsed out. If we wanted to parse out the domain only from each URL, we could select the host key. It's much like using parse JSON, where we can place a period, then the name of the key we want to parse. When we rerun this query with a key defined, we see the domain field has the parsed domains from each link. When we examine the schema, we see that the parse URL changed the data type to dynamic in the same way that parse JSON did. If we needed to summarize this data and we need to take it back to a string data type, we can incorporate that in the same record like this. Everything in the parentheses will be run as dynamic. Then the toString function will be applied. As we rerun the query, we can see that the data type is now changed back to a string. Keep in mind that as your datasets grow, some parsing functions can take a long time to finish, as some may fail to complete the function at all, depending on the size of the dataset. So it's best to filter the output first, so you're only performing the parsing function on the records that you need. Let's move on and sample a new table called File Creation Events. Let's narrow down our filter to distinct paths where files were created on host devices. For this example, we'll just take a sample of 100 records. If we want to parse out different values from this field, we can use parse path. When we place the name of the field we want to parse in the parentheses and run the query, we can see it also creates a JSON with key value pairs in set patterns, just like parse URL. We can then select different keys we're interested in. Let's parse out the root path, directory path, file name, and extension. We can see each section is now easily parsed out, and we can filter on these fields more easily. When we look at the schema, we can see that all the parsed out fields are set to dynamic. If we wanted to parse out all the fields, we could also choose to use evaluate bag unpack like this. The advantage here is that all the fields are automatically in a string data type, so there's no need to transition back from dynamic if you need to use distinct or to perform summarizations. Another common piece of information that's useful in a digital investigation is the user agent. Let's go to the outbound network traffic table and take a sample. We can see which IP sent the traffic, whether it was a GET or POST method, the URL that was navigated to, and the user agent that facilitated the traffic. There are multiple elements embedded in each user agent, and we can parse those elements out of the string using the parse user agent function. We have three parsing options to choose from. One is the browser information, one is the operating system information, and the last one is the device information. If we start out with the browser, we can see it parses out all the relevant browser information. You can also see that there's a nested JSON, so if we need to parse out specific keys, such as the family, we can refer back to our parsing nested JSON lesson, and we can parse it in this way. If we want to parse out the operating system from the user agent, we could change it from browser to OS. If we wanted to parse out the operating system type, we could do it like this. Lastly, if we wanted to parse out the device information, we could change OS to device. But this may not be available in all user agent types depending on the data set you're working with. Sometimes we have a string and we want to add something to each record in the field. When we need to add characters to an existing string, we can use strcat. This is short for string concatenation. First, let's look at the employees table, and we'll isolate the username and company domain fields. If we wanted to create a new field that joins the two fields together, we can use the string concatenation function. First, we extend a new field and give it an appropriate title. We use the strcat function, and in this scenario, we can place the name of the field first, a comma, then the name of the second field. When we run this query, we can see that the strings in the two fields are now joined. If we wanted to add an @ symbol between the two strings, we can add it in with quotes like this. When we rerun the query, we can see it added an @ symbol between the two strings. Now that we know how to add things to strings, let's see how we can take things away from strings. Let's go back to our original two columns. In this example, we want to take away the .med at the end of the company domain. We can use the trim function to take characters out of a string. There are three variations of trim. The regular trim function removes all the characters that you define from either the front or the back of the string. Trim_start only removes the characters you specify from the beginning of the string, and trim_end removes the characters from the end of the string only. In our example, if we want to remove the .med, which is at the end of each string, we can use trim_end. We need two arguments in the parentheses. When we look at Intelisense, it helps us remember what the two arguments are. The first argument defines what we want to take away. In this case, we want to take away .med, and it's in a string, so we put it in quotes. We place a comma, then define the second argument, which is where we want to take it away from. In this case, we want to apply it to all items in the company domain field. When we execute this query, we can see it gave the expected output. When you have a character or group of characters in a string that you want to identify and substitute, we can use replace. When we look at the employees table, we can see a field for email addresses in the fictitious company of Castle and Sand. Let's focus on that field and replace all of the instances of .com with .net by using the replace function. When we extend a new field and type in replace, we have several options. Since this field is a string data type, for now let's type in replace_string. The parentheses have three arguments. The first is where you want to perform the replace function, and in this case, it's in the email address field. Next, we place what we want to be replaced, and lastly, what we want to replace it with. When we execute this query, we can see the changes were made rapidly on 1,500 records. In our next example, we're looking at the file creation events table and projecting only unique host names. We see a normal pattern of some numbers and letters, followed by a hyphen, followed by the machine type. In this example, we want to divide the field. Our goal is that we only have the machine type in one field. We can use the split function for this task. We can extend a new column and type in the split function. Our arguments will be where we want to perform the split and what we want to split on. In this case, we can split on the hyphen. We can see the output is in the form of an array in which there are two string objects. Do you remember how to parse an array? In this case, we can use parse JSON and reference the index value of 1 to represent the second object in the array. If we wanted to summarize or use distinct on the output, we'd get an error because the data type is currently dynamic. So if we wanted to perform those actions, we can change the output back to a string like this. When we rerun the query, we can see the machine type field is reset to a string, and we can perform a summarization on the field without error. There may be times when we need to make the letters in a field either all uppercase or all lowercase. In this situation, we can use either to upper or to lower. As we extend a new field, we simply type in to lower and place the name of the field of interest, and it performs the expected output. When we change the function to upper, we can see the output is now in uppercase. In the beginner series, we talked about using double equals, has, and contains to find and filter for items of interest. Each has a different level of precision and requires different levels of resources to execute. These take care of most of our searching and filtering needs. If we need more options beyond a basic string search, we can use regex. Regex is short for regular expression and can be used to find or find and replace patterns in a string. There are many forms of regex, and KQL supports the RE2 form. You can conceptualize regex as its own language, and RE2 as a dialect of that language with unique syntax. As an example, let's go back to the process events table and look at distinct host names. We could easily search for exact matches using double equals. We could match on the machine type after the hyphen because it's a delimiter using has, or we can match on substrings using contains. What if we need to find host names with no numbers in them? In this case, we could use matches regex to assist us. We can use where to filter, then use matches regex with a space between the two words. In the quotes, we can place our regex statement. When we run this query, we can see it's filtered for host names without any numbers in them. Regex is a powerful tool for finding patterns using matches regex, but it can take considerable resources in some use cases. The initial caret symbol indicates the beginning of the line, and the dollar symbol indicates the end of the line. Next, we have brackets, which mean a character class. In this case, the 0 to 9 references numbers. The caret before the numbers is a negative, so think of it like an exclamation point in KQL. Up to this point, we're just saying no numbers. The asterisk means that the pattern we identify can appear in any number of characters in the field. There are also many different ways to write a regex-based statement and get the same results, since the language also has shortcut symbols. Let's move on to base 64 decoding. We can see that one unique PowerShell base 64 encoded string is found in the environment. In this case, we want to extract the actual base 64 string into its own field. We can first extend a new field and use the extract function. Since we're using regex here, we need to place the first dash and include all possible encoding aliases in PowerShell to find, then extract everything after the encoding. After the comma, we see the number 2. This represents the capture group we're interested in extracting. In this case, the first capture group would be one of the encoding aliases, and the second capture group would be everything after that. So we select 2 for the second group. Lastly, we identify the field to execute this in. When we run this query, we can see the extracted base 64 is now in its own field. But there's one problem. There's a quote at the end, which is not part of the base 64. So let's remove that with a trim end function. Now that it's cleaned up, we have the base 64 string isolated. If we wanted to decode the base 64 string to identify what is being executed, KQL has a base 64 decode toString function to help us out. When we run this final query, we can see the decoded string and better understand what is being executed. In this case, the command uses PowerShell to call a WMI method to install software updates on a machine. While this is likely benign in nature, it may be something to look further into. Let's transition to working with IP addresses in KQL. We can use the IPv4 isPrivate function. This gives us a true-false value whether or not the IP is internal. As we extend a new field and use the new function, we simply place the field we want to conduct the true-false evaluation in the parentheses, which in this case is the src_IP field. When we run this query, we can see that some are true and some are false. If we want to identify a range of IPs, then identify if the IPs in our dataset are in that range, we can use the IPv4 isInRange function. We can define which field to analyze, then define the range, and we receive a true-false value. If we need the subnet mask to be parsed out and identified, you can use the IPv4 netmask suffix function. If no subnet mask is present in the field, the default will be a mask of 32. If we have a list of IPs and we want to associate a geolocation with each IP, we can use the geoInfoFromIP_addresses function. Keep in mind that the geolocations associated with IP addresses are not precise and should not be trusted as an authoritative source of location. You can see that internal IP addresses do not present a location value, but public IPs do in a JSON format with a country, state, city, and lat-long keys with associated values when they're known. When we check the schema, we can see that the JSON is already in a dynamic data type, so it's ready to be parsed. We can easily use evaluateBagUnpack to parse the keys into their own fields for filtering. We can also summarize a count by country. When we look at IP addresses, they're in dotted decimal notation, and they consist of 4 octets separated by periods. If you need to convert to a big endian version of the IP to be used in calculations or for comparisons, KQL has a function for this. This conversion takes all the binary values of each of the 4 octets and it concatenates them all together, making one long binary string of all 4 octets. Each octet is multiplied by a specific exponent to create a final value. If the big endian number is needed, we can use parse IPv4. You may have a starting IP and an ending IP associated with a range of IPs and want to find all the potential CIDR ranges possible. In this case, we can use the IPv4 range to CIDR list function. In this case, we're just creating a new field with a start and end IP for our range. When we run this query, we see the potential subnets in that range. This could be useful for network admins that need to configure subnets within a given range. In addition to the IPv4 functions shown in this session, KQL also has functions for IPv6. We can transition to Evaluate Pivot next. As we take a sample of sign-in logs, we can see many different fields of interest. But scrolling through them all left to right doesn't present well. As we narrow it down to a single record of interest using argmax, our goal is to capture this information in the best way for case notes. Using Evaluate with a narrow function places each column as its own record in a key value pair format. This may be what we need already, but we can make this data even more presentable by removing the initial field full of zeros and adding a colon after the column values. Sometimes when we write complex KQL queries, we need to call on the same data set multiple times. If a data set logs a high volume of records, there may be additional records added from the first pool to the second pool, which can lead to data errors. Pulling the same data set twice when not needed also requires additional resources and increases the likelihood of the query timing out, depending on the size of the data and the system used to query the data. Instead of calling the same data set multiple times, we can pull the data once and save it in a temporary state, then call the same saved data set again later in the query. In this case, we can use the materialize function to save our data set that we plan to reuse. We can create a variable for our saved subquery in this general format. The subquery portion represents any query that you'd like to save as a temporary output table. In this use case, let's first create a query that we'll use as our snapshot. In this example, we want to take a snapshot of all sign-ins in the last week. We made changes in our environment several weeks ago, and we want to look for applications and resources no longer having authentication attempts or success. If we had to call this data more than once, it's possible new sign-in records could have been logged, skewing the results. When we run our subquery, we see it gives us a snapshot of sign-in activity in the last week. We can now place this query we want to use in our materialize function. There are many stylistic choices here to make the code more readable. One option you may see is having the initial function parentheses on one line, indenting the subquery, and placing the closing parentheses and semicolon on the far left, so it can be more easily identified as the end of the subquery. This is personal preference, however, and it's not required for the subquery to work properly. Placing the closing parentheses and the semicolon on the same line is also common. We can now write the rest of the query and refer back to the saved snapshot as needed multiple times without additional records being written. In this case, we can create three variables, one for result type, one for app display name, and one for resource display name. We can then extend some new fields that provide a true-false value, whether or not the apps, resources, or error codes are in our data snapshot. If the value is true, then the apps or resources were seen in the baseline period, but were not seen in the last week. Or we could easily reverse this query and identify new apps and resources that are being used in the last week that were not used in the baseline period. When we use materialize, keep in mind that there's a maximum cache of 5 gigabytes of data. So if you're working with large data sets, you may need to rewrite your query using different strategies like distinct or argmax. If we were working with a large data set, in this use case, we could further optimize the query by taking out the time-generated field and changing project to distinct to narrow down the initial snapshot results to only unique values. Another good use case for materialize is unioning two tables together. You might want to take a snapshot of a table, then run multiple different calculations on the same data to see the different outputs, then union the data back together. Materialize is great for these types of use cases, but keep in mind that using materialize when it's not needed may actually use more resources than not using it at all. When we string together multiple sets of instructions inside of a query, we can save it as a variable. That variable can be called for the life of a query. But if we need to use the same sequence in a different query, we need to redefine the variable. Functions can be a way to save and later call the same set of instructions in any query we want. Let's try a sample use case. We want to create a function that will provide the square of a number. We want to call the function square. We want to be able to use this new function in any query moving forward without having to rewrite it. And we want to be able to change the logic of a function in a single place and have it propagate to other queries. In order to create functions, you need to have the ability to write, or you'll get an error. When we write this function and execute it, we can see each component is listed in unique fields within a record. When we expand the database and expand functions, we can see the newly created math functions folder that we defined earlier. Inside of the folder, we see our newly created square function with an fx before it. We also cast the input value of the square function to a real data type. Let's test out this new function and see how it works. We can use print result, then place an equals, then use the function with a number in parentheses. We can see the output is 36, which is 6 times 6. When we created the function, we cast the input to a real data type. Let's see what happens if we place a number with a decimal in the function. We can see that the output is modified. If we want to modify the function and cast it to an integer instead of a real data type, we can. If we simply change the data type to int and rerun the line, it gives an error, saying it can't be executed because it already exists. If we change the first part from .create to .create or alter, it will allow us to modify the existing function. Now let's test out the modified function with a value of 6. Then the value of 6.1. What happens if we use 6.9? And finally 7. We can see that the output rounds down to the nearest integer. We could also create KQL functions for converting Fahrenheit to Celsius, or other types of functions commonly used in our work environment. That's all for the 10-minute KQL reference guide. If you find value in these videos, please give it a like or a share. And if you want to be notified of more KQL content, click the subscribe button with the notification bell.